Good morning, everybody. It's a great pleasure for me to give this talk this morning. Hopes and challenges for information science in cosmology. The first question that you may have in mind is, of course, well, why am I going to talk about information science at all? So as a disclaimer, there will be no physics results in this talk. And also, I was actually a little bit bored about talking about my good old stuff. So I've tried to do something slightly different, in particular, some historical perspective and discussions about what's waiting for us in the field. So first question then, why information science? Information science, but what for? So this is the motivation part for cosmology. So let's first have a look at the big picture. Everybody in this room, I guess, knows what I'm talking about here. But then again, on the left, observations of the cosmic microwave background by the Planck satellite, something which looks smooth and homogeneous if you look at the large scales, but these very small glitches here at small scales, which are extremely informative about the cosmological model. If you continue to zoom in, that's the large scale distribution of galaxies in the universe. And again, something which is homogeneous on the large scales, but which sees structures on smaller scales with this network that you see of filaments and sheets connecting clusters and sheets surrounding larger, emptier regions known as cosmic vaults. So this is what we see in observations. Now, what do we want to do with that? Well, the large-scale structure is potentially a big source of knowledge, a very vast source of knowledge about cosmological parameters to test our standard model lambda CDM and test it against alternative, the physical nature of the dark components, dark matter and dark energy, neutrinos, and the number and masses of neutrinos, the geometry of the universe, tests of the standard picture for gravity, which is general relativity, initial conditions and linked to high energy astrophysics. That's for the cosmology part. Also some astrophysics, and that's mostly linked to galaxy formation and galaxy evolution as a function of their environment. So here we care about galaxy properties, color, chemical composition, shapes as a function of the environment, and effects such as intrinsic alignment and intrinsic size magnitude correlations, which are very important in particular if we want to understand weak gravitational lensing. Right, so let's have a look at the roadmap. This is essentially the status of our last current and upcoming experiments with DESI, which started about a year ago, Euclid, which hopefully will be launched next year, as we have learned yesterday, the Rubin observations from the ground and from LSST, and then the Raman Space Telescope, so spectroscopic surveys in blue, photometric surveys in green. And we expect about typically a petabyte of data, of raw data for each of these experiments. So the question is then, what are we going to do with that? Right, so let's then now talk about information sciences. So the first thing is, well, first things first, the forward problem. How do we go from theory to data? And here we have to talk a little bit about data models and computer models, in particular, numerical data models in light of what's currently happening with computer hardware. So the thing is that traditional hardware architectures are reaching their physical limit. That means that this is really linked to quantum mechanics, the properties of silicium, etc. That means essentially that per core compute performance is now slowing down. It used to be very quick here. No, that's something known as Moore's law, and this is basically plateauing for about the last few years. Now, there's still development in hardware, of course, and now hardware doesn't focus on improving individual cores, but on packing a larger number of cores into each computing processing unit. That's typically 10 to the 5 cores now in current supercomputers, soon 10 to the 6 and 10 to the 7. That's known as the exascale world. So larger number of cores, and also now using hybrid architectures, which are made of not only cores, but also material accelerators, such as graphical processing units. Here they are, or even reconfigurable chips. That's FPGAs, the field programmable gate arrays, or even once you've programmed something on FPGA and really convinced that this is what you want in the end, you can make a dedicated chip, and that's the ASICs, the application-specific integrated circuits. Right, so all of this means that it used to be true that basically to run a bigger cosmological simulation, we just had to wait for computers to get bigger themselves. That's not quite true anymore. It means that numerical data models cannot now merely rely on computers becoming faster in order to reduce the computational time. Well, then again, a challenge for parallelization of n-body codes in particular, if I look only here at the gravity problem, compute cycles are no longer the scarce resource. That means that the cost is now driven by interconnections. And now we have Amdahl's law, which states that essentially the latency in these interconnections, the latency in communication between cores, is going to kill the gains of parallelization. So that depends always, of course, on the parallel portion of your code. You have here the speed up as a function of the number of processes. It's always going to plateau somewhere. But the maximum speedup that you can reach essentially depends quite a lot on the fraction of serial, the remainder of the serial fraction of your code that remains. And this is why most of the work on numerical cosmology so far has focused on improving the algorithms. So cosmological simulations started here, n-body simulations here started by these points here. That's the direct summation, directly solving the n-square problem. And this is something which improves actually fairly quickly due to the intrinsically n-square nature of the problem. That's the green dots here. But you have this full cloud of dots here of algorithms that use essentially approximations in order to compute the gravity field, such as tree, multiple mesh methods, etc. So they tend to drastically reduce the need for communications across the full computational volume. And this is why cosmological simulations have been able to essentially follow Moore's law here of 59% per year. Actually, even a slightly super exponential trend, you may argue, for the last few years. All of the references are here on my website if interested. So in this context, let me advertise one idea, which I think could be useful for these numerical data models in the future. This idea is to try and run perfectly parallel cosmological simulations. So the idea is based on the following. We have an analytical solution which is actually fairly good at large scales. And so it seems a little bit silly to run a full numerical solver where we could use the analytical solution on large scales. So essentially the story is, can we build a framework, which means that in order to solve for the accelerations here, we have this non-local term here coming from the full gravity field. Now, can we just make a change of frame of reference and use the large-scale analytical solution? So if we place ourselves in this new frame of reference, then the source term here becomes local, and that means that we can essentially run sub-boxes of the full simulation box, and then stitch together all of the pieces. All of this within some degree of accuracy. So this is a framework called spatial co-moving Lagrangian acceleration, SCOLA, because that frame of reference here is computed by Lagrangian perturbation theory. Right, so, well, these were my comments about information science as applied to the forward problem. So now let's talk about the inverse problem and going from data to theory. And I'm going to adopt for this Bayesian point of view. So first thing first, why Bayesian inference? Well, this is my personal view about that. The inference of signals is typically a very ill-posed problem, and that's the case particularly for cosmology. We have incomplete observations, we have survey geometry, a mask on the sky, not the full sky is observed. We have selection effects in the radial direction. We also have noise, biases, systematic effects. And there's even actually cosmic variance, which is a source of uncertainty, which is in this case specific to cosmology. That's the fact that we basically just have one universe to observe. So we have these forward models. I talked about that a bit earlier. Now, how do we make the connection with observations? And all of these sources of uncertainty mean that, in my view, no unique recovery is possible, and we need to adopt a statistical approach. Another comment about why we should use Bayesian inference is that there's a natural progression in cosmology about the complication of the problems we've been talking about. So observation of the homogeneous and isotropic expansion, supernovae, then anisotropies of linear perturbation, the supernovae problem, yes. Then anisotropies of linear perturbations, that was the cosmic microwave background, and we are now trying to extract the full information from the non-linearly evolved cosmic structure. So at small scales and at late times in galaxy surveys. So essentially a progression in the kind of problem we are talking about, which has to be matched by a progression in the statistical methods. Some additional challenges for next generation data means that always the difficult data analysis questions or the hints for new physics will first always show up as tensions between measurements. And we will need to characterize these tensions. Are they real physical effects? Or are they artifacts due to our flaws in our analysis, essentially? Additional challenge, of course, will come from nonlinearity. That's about 80% of the total signal, which will come from nonlinear structures. And from model misspecification, because next generation surveys will be dominated by typically unknown systematics, not only known systematics, but unknown systematics. Right, so a Bayesian approach, so Bayes' theorem, that's the only equation in my talk, essentially. Bayes' theorem is this statement about how we analyze evidence and how we change our minds as we get new information. I guess for this audience, I don't really have to comment on the terms here appearing. Just to show you the players in the field, Thomas Bayes. Actually, the formula was published after his death by his friend and editor, Richard Price, and was also discovered independently by French physicist Laplace in, I think it's 1774. As Guillaume said, I spent a few years in London, so I did my pilgrimage, and this is a picture that I took of Bayes' tomb. This is at Bunhill Fields, burial ground in the city of London. Right, so we have this formula. So, well, demonstration first. That's the joint probability of signal and data. First, equality by applying the definition of conditional probabilities. Second, equality by symmetry. Third, equality by the definition of conditional probabilities again. Done. Right? So now you may ask, well, okay, well, seriously, why should we use this, right? This is trivial and this is outdated. Furthermore, it actually measures belief. It says you can, in fact, learn from even missing or incomplete data, even from approximations, even sometimes from complete ignorance. So it really runs a counter to the conviction that science requires objectivity and precision. And this is why, for many scientists, after Laplace's death, Bayes' theorem, or Laplace theorem, was pronounced dead and buried. And yet, in many situations, Bayes' theorem helped solve practical world problems. So here is an incomplete list. It helped exonerate Alfred Dreyfus from miscarriage of justice. Thank you for the question. There are slides about that just coming up. Save the Bell telephone system from financial panic. Predict earthquakes and tsunamis. That's by Harold Jeffreys. Harold Jeffrey, whose name is also associated to Bayesian statistics. If you know about Jeffreys priors, for instance, he was also actually a geophysicist. Helped in the Second World War, direct Allied artillery fire, locate German submarines, the U-boats. Quite famously, break the German Navy's Enigma machine, the Enigma cipher. Alan Turing is very much associated to this story. Prove that smoking causes lung cancer, etc., etc. So many practical world applications. In fact, a book has actually been written about that. It's called The Theory That Would Not Die. Quite an interesting book. So the scientific battle lasted for about 150 years until computers arrived. And when computers arrived, Bayes' theorem was essentially adopted almost overnight because, well, suddenly it worked. And you find the end of this story essentially in James's book. where he writes, for instance, that James is quite an opinionated man. He writes in the introduction, the superiority of Bayesian methods is now a thoroughly demonstrated fact in 100 different areas. One can argue with a philosophy. It is not so easy to argue with a computer printout, which says to us, independently of all your philosophy, here are the facts of actual performance. And in fact, the end of that story is actually a mathematical theorem now. That's the Cox-James theorem, 1946. You find the definition again in the book. Essentially, it says that any system which is reasonable in the sense of manipulating plausibilities and consistent with a set of desiderata, Cox desiderata, any such system is isomorphic to actually Bayesian probability theory. So in plain English, not only this is a good way to, a good theory of learning, it is basically the only way to phrase it in a reasonable way. Right, so the Dreyfus affair, Henry. A little bit of history, because, well, now I have to tell you why Bayes' theorem was involved in the Dreyfus affair. So one slide about history, a reminder, if you're not familiar with the Dreyfus affair. So 1894 in Paris, Alfred Dreyfus is a man of Jewish descent. He is a captain in the French army, and he is convicted of spying for Germany on the basis of handwriting analysis on a sheet of paper which has been found at the German embassy. He is sentenced to public cashiering, dégradation publique, and a life sentence in the penal colony of Devil's Island, l'île du Diable, Bagne de Cayenne in French Guiana, which, as the name indicates, is not a very pleasant place for your holidays. So 1896 to 1898, some new evidence comes to light, which identifies the real culprit, a man named Esterhazy, who is actually acquitted. And that is when essentially a few people decide that enough is enough. And among these people, you find famously novelist Émile Zola, who publishes an open letter to the President of the Republic, which was titled J'accuse and published on the front page of the newspaper L'Aurore, where he writes in particular, I accuse the army of having carried out a villainous investigation, by which I mean an investigation of the most monstrous partiality. I accuse the 3 handwriting experts of having made deceitful and fraudulent reports. So after this, 1899, Dreyfus is tried again for a second time. And well, surprisingly or not, he is convicted again. He is sentenced to 10 years imprisonment. So he is pardoned and released right after the trial, but he is not cleared. And the story lasts for a few more years until 1906, his final rehabilitation, Dreyfus is finally exonerated from all charges and reinstated as a chef d'escadron, that's a commandant or major in the French army. Right, so, well, why is that related to probability theory? I first need to tell you that central to the incrimination was something called the system Bertillon, which is based on the name comes from Alphonse Bertillon, this man, who was a criminologist, and he actually invented the idea here of taking pictures of criminals like this with the profile and face on. That is why. So Bertillon was a criminologist and invented the system Bertillon, which is based on graphology and probability calculus, which attempted to prove that Dreyfus had disguised his handwriting by imitating his own handwriting, something he called auto-forgery. So the idea goes pretty far, as you can see. So during the trial, the second trial in 1899 in Rennes, 2 mathematicians were called as witnesses, Jacques Hadamard, that's mostly because he had some personal links with Dreyfus, but also Paul Painlevé in his quality as mathematician. And Paul Painlevé then after that actually became a politician and was in fact a prime minister, président du Conseil in France. So they were called as witnesses, and in particular, Painlevé read to the court a letter by Henri Poincaré. So Henri Poincaré writes to Painlevé. So he writes essentially, if you can read the French version, by the way, I invite you to read the French version rather than listening to what I'm saying here. So he writes, my dear friend, you're asking me my opinion about the system Bertillon. Of course, on the essence of the affair, I can't say anything. But if you're only asking me my opinion about the calculation of probabilities, then I can give you my opinion. Then he goes on to explain that out of 26 possible coincidences on the sheet of paper, 4 are realized. Assuming the probability of a coincidence to be 0.2, Bertillon concludes that the probability of the event is 0.2 power 4, which is this number here. And he writes, this is wrong. this colossal mistake makes everything that follows suspect, right? So in fact, well, Poincaré obviously knew very well that you had to apply here a binomial distribution rather than just taking the power 4 of the exponents. So 4 coincidences out of 26 with a probability of 0.2. Now, as a side comment, actually, it's not exactly clear to me what Poincaré calculated to find this 0.7 here, because if I make the same calculation here for exactly 4 coincidences, the number is actually 0.17 here. Or maybe I can assume that the sentence is actually slightly ambiguous here in French, so I can assume that maybe Poincaré meant at least 4 coincidences out of 26, in which case the number is 0.79. Sorry? That's a letter from Poincaré written to Painlevé. Yes. So Poincaré is reading the letter to the court, written to him. Painlevé is reading the letter written by Poincaré to him. Well, so that's the first piece of probability involved. Now, second thing is during the final trial, 1906, this is where Bayes' theorem appears. So here essentially boils down to what's known as the prosecutor fallacy. Essentially, the prosecutor's fallacy is that whenever you have a trial which involves probability, the prosecutor's argument essentially boils down to this. An unlikely event has happened. What would be the probability of this unlikely event if the accused were innocent? Low. Therefore, they have to be guilty. And as you are now familiar with Bayesian statistics, you know that this is not the right question to ask, of course. The question is, given that this unlikely event has happened, what is the probability that they are guilty? So 3 mathematicians were mandated by the court to write a report, which essentially shattered the système Bertillon. That's Poincaré again, helped by Gaston Darboux and Paul Appel. All of these people were involved as mathematicians here in the Sorbonne. And here in the introduction of their report, it starts by some notions about the probability of causes. So they talk about how to pick balls in a jar, I think white and black balls, and then write, the problem that concerns us here is of the same nature. The effect is known. It is the coincidences noted on the bordereau. That's the sheet of paper that's we talk about. And it is the codes, forgery or natural writing that must be determined. It is therefore the so-called formulas for the probability of causes that should be applied. That's now with what we call Bayes formula. But the application of this formula requires some care. Then they go on to be able to calculate following an observed event the probability of a cause. We need several data. It is necessary to know what a priori before the event the probability of this cause. And it is necessary to know what would be for each of the possible causes the probability of the observed event. That's what in modern parlance we call a prior and the likelihood of all the events, which allows you to normalize and compute the evidence. Right, there's much more actually in this report which shattered the système Bertillon about what they call the prior choice for what they call moral sciences, about confirmation bias, about the look elsewhere effect. So I have like 100 backup slides on this if you want to ask me questions. But let's go on and let's go back to some cosmology. I just wanted to show you now that I've convinced you that Bayes' theorem is interesting, that it's still useful today, and that's an advertisement slide about Borg, Bayesian origin reconstruction from galaxies, for which the IAP is one of the birthplaces. This is essentially how it works. You have observations here on the right, reconstructions of the initial conditions and final conditions here, which are linked by gravity. And what you're looking at here are each image is one sample of the posterior PDF. So that's quite and this is what quantifies uncertainty. So that's quite a large scale application, 17 million parameters, 1.5 million CPU hours. But this is really nothing more than Bayes' theorem. Now, can we go a bit further with this inverse problem? And we can ask ourselves, well, with Bayes' theorem, we know essentially how to learn, but how much can we learn? And this is where I have to introduce the notion of information in probability theory. So the Fisher information in particular measures the amount of information that a random variable contains about an unknown parameter. That's essentially how it works. If you have small Fisher information here, that means that the curvature here of your likelihood at the peak is high. That's a flat likelihood peak. So you have then large variance and low accuracy on your final parameters. Conversely, if you have large Fisher information, that's a sharp likelihood peak, small curvature. So that's small variance and high accuracy. Now, if you actually generalize this notion, then that yields the field of information geometry. First question that you can ask is, if you have one point and which is drawn from a distribution, how unlikely is it that you draw this point from the distribution? And this is where you have to take into account something known as Mahalanobis distance, which measures the distance between a point and a distribution, essentially, probably. And for a multidimensional problem, the Fisher information generalizes to a matrix, the Fisher information matrix, and it defines a metric, the Fisher-Rao metric. And here it's interesting to see that in information geometry, actually many of the tools that appear in general relativity are used. For instance, the notion of connection, the notion of the Christoffel symbols, the notion of metric, the notion of geodesics, etc., etc. In fact, I actually found a quote by Rao where he comes back on his work and he said, I suggested the differential geometric approach in my 1945 paper by considering the space of probability distributions. I used Fisher information matrix in defining the metric, so it was called the Fisher-Rao metric. And differential geometry was not well known at that time. And in order to compute the geodesic distance from the metric, I had to learn the mathematics from paper on relativity describing Einstein metric. It was only 30 years later that my work received attention. And one more thing about probability theory, then again, an example about why proper statistics matter. We are at the end of the 19th century. We have Gibbs canonical and grand canonical ensembles, which are derived from the maximum entropy principle. And these theoretical predictions, they fail to correctly predict the real thermodynamic properties of these real physical systems. In fact, the predicted entropies are always larger than the observed ones, which means that, well, there must exist additional microphysical constraints. And that's where ideas such as the discreteness of energy levels came. First for radiation, then for solids, then for individual atoms, etc., and then the development of quantum mechanics. So my point here is that the first clues actually indicated the need for quantum physics were actually uncovered by seemingly unsuccessful applications of statistics. Now, the notion the information theoretic notion which generalizes or which, let's say, which mimics entropy, physical entropy in information theory is known as information entropy. That was developed by Shannon in a very important paper in 1948, where he actually, well, he essentially both introduced the field of information theory and solved most of its problems. And actually, for this reason, this is a picture that I took at the Science Museum in South Kensington, and they think the entire paper is worth being in the museum, which I think I quite agree with this point of view. So yeah, that's Shannon, 1948. Interesting discussion between von Neumann and Shannon about this name for missing information. I think the word entropy doesn't appear in the paper. It says, well, why don't you call it entropy? In the first place, a mathematical development very much like yours already exists in Boltzmann's statistical mechanics. And in the second place, no one understands entropy very well. So in any discussion, you will be in a position of advantage. I found that one first. Right, so applications of this, current applications of these ideas in cosmology. And here I have to talk a bit about Bayesian experimental design. Bayesian experimental design is where you try to have information optimal or entropy maximal criterion for whatever you want to do. For instance, acquisition of future cosmological data. So for instance, this is a map of the universe, and this is where to look if you want to measure cosmological parameters of lambda CDM. You have the map essentially of how informative regions should be about cosmological parameters. That's a map of the Fisher information for perturbative changes in the cosmological model. If you're interested about dark energy, well, this is where to look in the cosmic web if you want to learn about dark energy, because dark energy affects the filaments, it affects the growth of voids, etc. So it should have different amounts of information depending on where you look in the cosmic web. So that's the Jensen-Shannon divergence, which is very much linked to the notion of entropy in information theory. So Jensen-Shannon divergence between cosmic web type posteriors in different values, for different values of the dark energy equation of state. And this is what's quantified in Shannons or bits, but I tend to argue that a bit is actually the computer representation of a Shannon. So the Shannon is the more precise terminology. And finally, My last part is about what I call the imitation problem. That's a tribute to Alan Turing, who was talking about the imitation game. With now rising AI and machine learning, I haven't talked about that yet, but with these new algorithms in AI and machine learning, can we go beyond blind oracles? So some examples of AI in 2022. You can build funny things, such as, for instance, a binary political classifier. Here on the left-right scale. In France, by the way, left is red and blue is right. So there are things that are fairly uncontroversial. For instance, job security for young researchers, that's clearly left-wing. A short and precarious postdoc, clearly right-wing. But you have maybe some more surprising things, like cosmology is left and artificial intelligence is right. Bayes' theorem is neither left nor right. Data science is left. Information science is right. I'll let you try and make your own opinion about that. Or things such as text conditional image generation. And here, actually, I take the opportunity to say that all of the pictures that I've shown so far are actually AI generated. You just have to input some words, and that's what it gets for you. A cosmological simulation, an exascale supercomputer. Here, it had to fill only this part. I wrote a painting of a scientist among astronomical instruments, or cats, etc. It's very much trained on cats, so it works fairly well for cats. Right, so history again. Well, the birth of AI, where does it come from? It's actually fairly difficult to find the beginning of AI. But you can find the place where the term artificial intelligence first appeared. And that's actually for what was known as the Dartmouth Summer Research Project. What's interesting is to look at the proposal for this summer school, which tells you first that, well, people had to write proposals already back then. But also they write some pretty interesting things. So they write, the study is to proceed on the basis of the conjecture that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. An attempt will be made to find how to make machines use language, form abstractions and concepts, solve kinds of problems now reserved for humans, and improve themselves. And we think that significant advance can be made if one or more of these problems are, if carefully selected group of scientists work on it together for a sum. Right, so now modern AI. Well, some metaphors first to try and classify these AI algorithms. You can always build some analogies with other fields essentially of science. So first thing is analogies with classical theories of learning. And this is where you find things such as rule-based model, deterministic ones, case-based reasoning, learning by practice or chunking. There where you find also reinforcement learning, which gives you a reward or a penalty depending on the outcome. And this is when you close the loop and train again. You find also there non-supervised learning, for instance, autoencoders. Analogies also with the functioning of the brain. So for instance, the artificial neuron or the perceptron that started actually fairly early in the 1940s and 1950s. But then adding more and more layers essentially of these artificial neurons, that's the multi-layer perceptrons, notions of gradient backpropagation, etc. And now, of course, the very popular and fashionable deep learning and convolutional neural networks, which are a very big part now of artificial intelligence. But I can also use this point, this slide here, to make the point that, well, this is not only what there is in artificial intelligence. Analogies with nature also, and the theory of evolution with genetic algorithms. Culture also, epistemology with the theories of scientific discovery. How do you actually make scientific discoveries? Notions such as ontologies, which appear, for instance, in classifying, in text analysis and in semantic web analysis. And finally, of course, for us, analogies with physics, with statistical mechanics, with thermodynamics, with quantum physics. This is where you find things such as decision trees, Bayesian networks, graphs, Hamiltonian Monte Carlo, which uses Hamiltonian dynamics to explore probabilities, information theory and distributed AI, hidden Markov models, etc. So here are for the metaphors. Now, methodology. Well, essentially, you can classify these into two broad categories. You have First, symbolic AI, which is explainable, but typically costly. The word here was costly. This is where you find, for instance, the rule-based methods and the learning by practice. One neuron when it's alone, but only when it's alone. Things such as ontologies, decision trees, Hamiltonian Monte Carlo, hidden Markov models. Essentially, all of this is pretty much explainable, but costly. And you also have the second broad category, which is numerical AI, or so-called machine learning, which tends to be automatic, but very often is a little bit black box. And this is where you have things such as reinforcement learning, the multi-layer learning, deep learning, genetic algorithms also, which are not fully understood, etc., etc. Right. So, well, then again, why am I talking about that in a cosmology talk? So why machine learning for cosmology? So that was actually the subject of last year's conference. So I'm not going to do the conference in 1 hour, of course, or in the last few minutes I have even, I guess. So, but I can essentially try to summarize a few ideas which have been discussed there. First reason to use machine learning in cosmology, try to speed up and go beyond approximations. That's the field of building emulators. And here is one emulator, for instance, built by my former PhD student, Hari Mutuvalu, where he tried to bypass essentially the class code, the Boltzmann solver, which goes from parameters of lambda CDM to the power spectrum. This is something for which you can build an emulator out of Gaussian processes or neural networks if you want, which essentially provides some advantages such as faster calculation and gradients. Second idea is to try and find the information content. That's the field of automatic data compression. In particular, if you have field-based information and you want to find where the information is in there, then you can use deep layers here of deep learning, for instance, or several layers of learning in order to summarize this information and try to find the most informative summaries here, which keep as much as possible of the Fisher information. This idea was known as information maximizing neural networks. And finally, one last idea in which machine learning is involved is to build a posterior approximator, if you're interested in parameter inference, or build an evidence approximator, if you're interested in model comparison. And this is typically very much involved in the field of implicit likelihood inference or likelihood-free inference, where essentially we want to deal with these complex inference tasks in a cheaper way. So here is a try, for instance, where I use this algorithm called Bayesian optimization for likelihood-free inference, well, BOLFI, which tries to approximate here the banana, the yellow banana, which is the posterior for supernovae data analysis in the plane of dark energy versus cosmic matter content, and finds an approximation, the red posterior here for a cheaper computational cost. Last comment before concluding is, well, actually one more question. What makes a good AI or ML model? And this is where I want to talk about associative versus causal reasoning in scientific research. The story is that essentially with traditional machine learning, we obtain associative links between a latent space and data. But this doesn't mean we understand how nature works with only associative links. Just an example here based again on cosmology. Suppose you have two processes which generate the same power spectrum in the end. This is actual cosmic structure formation. And this is something different here simulated with just scrambling the phases. Turns out these two fields here have exactly the same power spectrum. So if I just look at this and obtain associative links between parameters and this, well, it's pretty sure that I haven't understood how gravity works, right? So that means, and this is my comment here on this point, is that means that purely data-driven machine learning may actually not be sufficient for research. And we need to go beyond that in two ways. First, with causally consistent generative or AI or machine learning models, if they have this causal consistency, then they actually naturally produce an explanation. And this is what you're looking for when you're talking about explainability. But also predictive models, predictive AI or predictive machine learning are assistance system for hypothesis generation. And hypothesis generation arguably is the first step towards scientific discovery. So just one example of this idea of hypothesis generation. This is an extension of Borg. That's Borg doing a machine-aided report of unknown data contaminations. With extending the model, now Borg actually automatically reports maps of unknown foreground contaminants. And when applied actually to SDSS3 data, Borg actually did find some unknown foreground contaminants. So this is the a posteriori power spectrum here from Borg as compared to the state of the art with backward modeling techniques, various techniques of mode subtraction, which takes into account various kinds of templates. And the interesting thing is to look here at what happens at large scales. We find no apparent contamination at these scales smaller than 10 to the -2. That means well beyond the turnover in the power spectrum. Whereas here with this traditional technique, well, we are basically unable to formulate any model which fits the data at these large scales. So what are these unknown foregrounds? Well, we still don't know, but at least we have now an hypothesis generator to try and investigate further. So I'm coming now to my conclusions. So I promised to discuss about hopes and challenges in information science for cosmology. So here are my take on this. So the forward problem first. Well, hopes, of course, numerical data models are now the new way to formulate theory. And we hope that it's actually a much more powerful way to formulate theory. Now, the challenge is, well, I've talked about it, scalability of these algorithms for the kind of problem we'll have to deal with. We could also talk actually about the energy cost of this, but that's a subject probably for a different conference. The inverse problem, hopes, well, Bayesian data analysis is now established, I think, on a stronger footing than ever. It's really established as a fundamental theory of learning. Challenges, well, contrary to maybe 100 years ago, a Bayesian model is not only a likelihood and a prior, and it has many external components. There are external components in these modern Bayesian models, in addition to the likelihood and prior, and we need control on these external components. Here I'm talking about, for instance, the training data or the posterior approximator. And that's quite challenging. And finally, the imitation problem, the AI and machine learning. Well, hopes is that, well, in short, fully machine-driven scientific discovery becomes now conceivable. Challenges involved is, of course, well, are we going to believe such scientific discoveries? So interpretability and explainability, proof and certifiability, etc. So as you can see, quite a few questions remain open. And one of these questions is actually, well, an important one. Where does this elephant come from? So I have some elements to answer this question, but I don't know the full story. So if you do, please let me know. And I think it's time to thank you for listening.
So it's now time for questions. Henry, you have the first one.
Yeah, can you just speak a bit more about hypothesis generation? Because that's like the most interesting thing in ML/AI. How does it work?
I think Guillaume would be the most qualified to talk about this since it's his paper, but I can try to answer this. Well, essentially here, well, you need something which is essentially you need to make the distinction between a fully physical model and a statistical model. Here we needed a model which actually fits the data in the end, and for that we had to introduce some additional parameters, call them nuisance parameters if you want, which allow us to fit the data in the end. So here specifically is to introduce foregrounds on the sky. So you have something which is assumed to be constant in angular patches on the sky. Sorry, it's constant in the radial direction, and it varies in the angular directions on the sky. And essentially, the machine is going to find what the intensity is in each of these patches in order to find a good fit in the end. And since, well, it turns out that this was enough to explain the data, it means that this effect is really something which is angular in the sky, and that's why we say it's an unknown foreground. Now, all of this needs, for the moment, user input, because we had an educated guess at the beginning that it was an unknown foreground. But we are moving towards really fully automatic hypothesis generation with this kind of ideas.
Other questions? Even online? So what's the status with Escola?
Well, the status with Escola, yes, thanks. Well, first I should say that there's a public code for anybody who wants to play with it. We had several areas of development actually. At some point, Ben suggested that we use this on his cosmology at home system, that's fully distributed computing, and try to use some smaller devices in order to compute these small simulation boxes. Even the hope was that anybody could actually learn a small simulation box in their mobile phone, and then we collect all of this and make big simulations out of that. And there are some more developments involved, such as light cones or additional physical effects, neutrinos, etc., which we'll work on in the future. Can also say, well, maybe that advertise a project I have with Declan, where we want to actually go beyond Lagrangian perturbation theory as the guess for the new frame of reference, but use a machine which is going to give us machine learning, essentially, to give us the guess for what the new frame of reference should be. And then the numerical solver will solve for deviations for any mistake, essentially, that the machine makes.
The question? Okay. And if there is nothing else,
wait.
There's question. Yeah, Alan.
Yes.
Alan, do you want to speak?
Yes, please. Really interesting talk. Thank you. I was wondering what your views were on any challenges for likelihood-free inference. You talk here on the slide that's up here about data contaminants. So the general area of model misspecification is a challenging one. And I wondered what your thoughts were about how difficult it is, or with likelihood-free inference. Is it harder than with these big Bayesian hierarchical models, would you say, or any particular challenges that might be difficult?
Yes, I think the problem of model misspecification is probably the biggest challenge facing likelihood-free inference. There's actually a bit of literature about that, with people trying to do some more conservative belief updates, not the full Bayesian update, but something which is more conservative than Bayes update in order to account for model misspecification. That's some approaches which try to generally answer the question. I have myself tried and have a look at this idea for specific cosmology problems, where the idea would be to have a look at latent variables which appear in the full Bayesian hierarchical model, rather than going directly for target parameters. For instance, you check the initial power spectrum based on your observations. If you're pleased with the initial power spectrum, then you go ahead and infer cosmological parameters. That was my contribution to the last maximum entropy conference in Paris.
But just as a follow-up, I mean, if in the likelihood-free cases, one often has to compress the data massively in order to do things, and I worry sometimes that might hide things, that bury things away, that mean that it's difficult to know what's going on.
Yes, I agree with you. Yes, that's yeah. I have no general solution for that, except making your model slightly more conservative in the first place.
Okay, thanks.
Yeah, I mean, if you want, so well, but so if nobody else has a question, no. Well, Henry was hinting that we should announce something. Well, I mean, as Florent announced, like in 2021, we did this machine learning conference at IAP. So we intend to do the same thing in most likely November of next year. So maybe you'll get more information on this. Cosmology, large-scale structure surveys, and machine learning. Okay, then maybe we shall close the session. And thanks, Florent, again.
Thank you very much.